If you are training or fine-tuning a large language model or a vision model or an audio model, typically you're going to be tracking loss. That's the cross-entropy loss, and it should be falling throughout the run. Maybe you're tracking it on a training set and also on a validation set. But something that is more practical and is a bit tricky to do but very useful is to measure performance on a benchmark during the training. So as your training progresses, you can measure performance on a Q&A benchmark or some other benchmark that you've defined. Now, this is easier said than done because during training, you don't normally auto-regressively decode tokens that provide an answer. I'll talk more about specifically what that means if you're not following, but suffice to say that calculating benchmarks on the fly during the training is not that trivial, but it's very useful if you can do it. So that's what I'm going to talk about today. It's called computing custom metrics. They're custom because they're in addition to the typical metrics that are reported by a trainer. And I'll talk about the trade-offs in different approaches, and then I'll go through a method where there is support for doing both training and custom metrics using unsloth and VLLM combined, but reading from the same model. So for this video, as an overview, I'll start off by describing what are some custom metrics and why might you want them. I'll talk about teacher-forced versus autoregressive decoding. Don't worry if you don't get that yet. You probably are familiar with this one, although you might not have heard of it being called teacher-forced. Then I'll talk about some training versus inference libraries. Libraries tend to specialize in one or the other, whereas here we actually need both, ideally combined. Then I'll talk about the options if you want to compute custom metrics during a training run. You can basically run a batch size of 1. You can stop training, compute metrics, and restart, or you can use an integrated method like unsloth's fast inference using VLLM. Why are they called custom compute metrics? It's because they're not the standard metrics that are reported. Typically, during a training, you will get back logs of, say, even the power usage of the GPU. You'll get back logs on the step number, and then you'll get the cross-entropy loss, which is a measure of how well the training predictions match the training data. The predictions match the training data. And as a standard, if you use a lot of unsloth libraries, a lot of notebooks or transformers notebooks, you'll nearly always have the training data set be evaluated in terms of cross-entropy loss. And then if you watch videos like I make, you might be encouraged to also use a validation set so that you can test if you're overfitting. So these are commonly reported metrics and are well supported by trainers. Now, custom metrics goes beyond this, and some examples I can give you. Because it's custom, it could really be anything. But one example is measuring the percentage correct on a Q&A data set. So during the training, measuring how many more questions the model gets right. You can see that as useful because if you know that you're getting more and more right during the training, it tells you maybe when you want to stop the training, or if you're starting to get less right, maybe you've overtrained, so you also want to stop the training and take the model where it peaked. Last of all, here, another example, you could have an LLM that generates code and you might be extracting and running that code. So you could generate metrics based on the output of that code if you are able to support custom metrics. Now, this is the crux of why custom metrics can be difficult, particularly metrics that involve having a complete answer. And the reason is because when you calculate cross-entropy, a standard metric, this involves doing teacher-forced decoding. Whereas when you do Q&A based benchmarking, you need autoregressive decoding. Now, what does that mean? We can take a look. And I've put together this little spreadsheet. Actually, I've got a copy over here. And imagine having a prompt. The quick brown fox jumped over the lazy dog. When you feed this in, you're going to get the language model to try and predict the next token in each case. And then you're going to compare it with the labels, which are going to be considered the ground truth. So the ground truth for the token after the is simply going to be quick. The ground truth for the token after brown is going to be fox. So you can see I can quite simply just copy over the whole range here by one cell. And now for the word the, I'm trying to predict quick and so on. So I've basically just left shifted my whole sequence here. And if you're working in the world of standard metrics, such as teacher-forced predictions, which is relevant for standard metrics, you're going to get the model to predict the next word after the. and maybe it's old, and then it's going to independently predict the next word after quick, conditioned on the history of then quick. So maybe here it does predict brown, and then the quick brown, it's going to predict the next word after brown, conditioned on the quick brown, and it's going to say monkey, for example. Then it's going to say the next word after fox, conditioned on the quick brown fox, and I'm going to say was. And hopefully you can notice the subtlety here of when I am making this prediction here, me as the model, I'm conditioning on the prompt, the full prompt. I'm not conditioning on the previous guesses. So when I read this across here, the teacher forced predictions, this is just nonsensical. It's old brown monkey was. I mean, maybe it kind of reads with some sense there, but the point is I'm not predicting was based on these tokens here. That would be autoregressive. So in autoregressive, if I fed in, for example, these 4 tokens here, and then I ask to start predicting here, I would say ran. And now if I continue autoregressively, I'm going to condition on these plus this, 2, and then I'm going to condition on this and this, there, and then I'm going to condition on this and this here, and store. So you can see here, this is autoregressive. I'm continuing the same sequence, whereas in teacher forced, I'm always going back to the prompt, and I'm passing forwards. And this teacher forced approach, which is the standard way to train, because then you basically compare the ground truth against the label. So you compare all of these and you calculate cross-entropy by comparing all of these here. This is quite an efficient way of doing a forward pass because you are basically able to do the forward pass from this forward here, these 2 forward to here, these 3 forward to here. There's nothing autoregressive about what's happening. In fact, if you're looking at a transformer, and in a transformer, you can kind of think of this as, here would be maybe a 3-layer transformer. If we fill it in like this, you're propagating down through the layers. And as you go down through the layers, you're able to actually fully calculate this layer for all of these tokens. So you can fully calculate this first transformer layer here. Then you can fully calculate this next transformer layer here. Then you can fully calculate this next transformer layer here. So this is really nice. You can just, in a single forward pass, go through the full training data. But if you do something autoregressive, this is not possible because now in your transformer, in order to get the word ran, you need to forward pass through all of these layers of the transformer. And you're not even able to start on the word 2. I mean, you can use some of the KV cache, but you're not able to start on the word 2 until you've got the word ran, because you've got to feed that in addition to the quick brown fox. So now you have to do another forward pass here, and then you have to do another forward pass here. This is called a decoding forward pass, and then another forward pass here. So when you autoregressively decode, you've got to have multiple steps. You can't just do one sweep down through the transformer here, a 3-layer transformer. You have to sweep down, and then you have to autoregressively decode. So the way that you do both of these things is different. This here is very reminiscent of doing training. So if I just merge this here, this is what happens during training. And this is much more like what happens during inference, because you're actually decoding and you're producing tokens. So this is much more like inference. And so the point is, if you want to have a full answer here, because remember, if you're doing a benchmark, not remember, but if you are doing a benchmark, you're going to have a question, and it's going to be something like, what is 1 plus 1? And then you're going to have an answer, and it's going to be 1 plus 1 is 2. And I'll spell that properly. But you need to autoregressively decode the full answer here. So anytime you're doing a benchmark, it's going to be a case of doing autoregression. Whereas when you're doing training for cross-entropy loss, comparing these ground truths with the teacher force predictions, that's just going to be a single forward pass. Okay, I've repeated myself enough here. So yeah, there's 2 types of decoding, and you actually need both to do custom metrics if your custom metrics depend on having full answers. And actually, this is why GRPO, you can watch my videos from earlier in the year if you wish, or other videos. GRPO, which was introduced by DeepSeek, it involves creating answers, assigning rewards based on the accuracy of those answers, and then using those rewards to update the weights. So in GRPO, you also need to roll out full responses, and that's why GRPO required a bit of work from the library makers like Transformers, like Unsloth. And we're actually going to leverage some of this capability that Unsloth, I think, introduced just because of GRPO, but also allows us to do both training and inference using the Unsloth library coupled with VLLM. So the problem with custom metrics is training libraries like transformers, like Unsloth, Axolotl, DeepSpeed, etc. And to be fair, I haven't deeply looked at DeepSpeed. Maybe there are some options there. But in principle, training libraries are focused on teacher force decoding, just single forward passes, whereas inference libraries support autoregressive decoding. So they will support doing this, these multiple steps. In fact, nowadays we're moving towards a world where you actually have GPUs dedicated to this. This is called prefill, the big forward pass, and then the subsequent decoding steps have got different GPUs. So you actually separate those, and DeepSeek talks about that. But yeah, inference libraries are specializing in this, and they also specialize in batching. Batching is more difficult when you are doing inference. That's because during training, as long as you have some sequences, like say you have another sequence that's up here and it just says the little girl was playing something like this in the house, and then maybe you have like a pad token here. So this, as long as you've got multiple sequences, you can just forward pass them all as a batch, and it's pretty straightforward. But the problem with inference is, in inference, you're not going to know exactly when your sequence ends. So you don't know when the end of the sentence comes. And so different batches. So if I put this like, let's just put in 2 batches here. If I feed in different batches like this, I don't in advance know where each of the batches finishes. And so you end up a lot of mismatches. You end up with sequences starting at different times, ending at different times. And so you need to do more dynamic batching where you can feed in kind of partial sequences and overlap them. And this continuous batching, it's called, this is a characteristic of good performance or necessary characteristic for inference libraries like VLLM or like SGLang. So the problem with custom metrics, I've said this a few times, but I'm hopefully getting deeper, is if you load both libraries. So if you say, right, I'm going to use transformers for doing my training and I'll use VLLM for inference, well, that means you've loaded a model with transformers and the same model a second time with VLLM. So you're going to take up much more memory. So yeah, doing these custom autoregressive metrics are a pain. That's why GRPO required library customization, adding in VLLM to Unsloth or to transformers. And where it leaves us if we want custom metrics is with 3 options. The first option is you just forgo any batching during inference and you just do simple single batch size inference at eval time. And you can do this already using Unsloth or transformers, but it's very slow because your batch size is 1. So you're not maximizing token throughput at all. You're not making use of the parallelization capabilities of GPUs. The other option is you can train, you can unload your model that you're training and load VLLM with the model. Then you can inference, do the evaluation, and then go back to training. So you can basically swap between the two. And this does work. It avoids the duplicate memory usage at once, but you waste a lot of time loading and unloading. And this is a problem if your models are big because they take a long time to load or unload or save. Also, your metrics become split because you've got training, eval, training, eval, training. So you're going to end up with your metrics split in multiple places. Now, there is one elegant solution, and there probably are others that I need to research more. But I think partly because of GRPO, Unsloth supports fast inference with VLLM. And here's how it does it. It loads a model using Unsloth transformers. And I call it Unsloth transformers because Unsloth is basically an improved version of transformers. It leans a lot on transformers. So it loads the model for training. Then it wires up VLLM to the same model in memory. So it avoids duplicating the memory. And this allows for simple forward passes for training and autoregression for inference with batch size larger than 1. So that's key. And the memory required, which will become relevant later, is going to be the model weights plus the lower adapter weights plus the training gradients plus optimizer states plus activations. But then also there is an allocation for VLLM's KV cache because VLLM is going to have to allocate a KV cache. It needs to store some of the historical KV cache for sequences to speed up decoding. So this is how Unsloth has kind of solved it with VLLM. It's quite an elegant solution. It does still take more memory for the reason I just said. And there's one other nuance before I go to actually demoing this in a script. Accelerate is a library that's often installed if you're using transformers or unsloth. It allows you to use multiple GPUs. It manages weights moving between different devices, including between CPU and GPU. And Accelerate is used to working with tensors, not with strings. So often you'll see the scripts when we try to work with inference at the same time as training, we end up having to work with tokens. And this means you will see places where we have to encode and decode a lot because we're not able to pass strings around as easily as you might think. So that's this theory portion of the video. I'm going to move now and show you this with a script. And it's in the advanced fine-tuning repo. If you go to trelis.com/advanced fine-tuning, you should be able to take a look at, well, you're already looking at this video, but I'll link the video here and you'll be able to purchase access membership to this repo or to the all access membership, which includes all of the Trelis repos that are currently published. So I'm going to go to the advanced fine-tuning repo and start up this GPU with a one-click template. And I'm going to use an A40 because I don't really need a lot of RAM. I'm not going to do a long training. I just want to show you what's happening. So I'm going to deploy this here and give it a second for the template to start up. It should git clone the advanced fine-tuning repo. You can check out one of my recent videos, which explains how to set up these templates. Note that in order to run the template, you do need to have set some environment variables via runpod secrets for your username, your email, your GitHub personal access token, and your Hugging Face Hub token. And make sure to give access to your GitHub personal access token to the repos that you are trying to clone if they are private. So I'll connect in here to Jupyter Lab, and I should see that the repo is being cloned, so I can head right into the fine-tuning scripts. So here I am, advanced fine-tuning, fine-tune, and then go down here to this unsloth custom metrics notebook here. Now I'm going to start the installation, and notice that as well as unsloth and VLLM, I'm also installing Google Generative AI just because I'm going to run some Q&A and I'm going to use Google as a judge of whether my answers are matching. Now, with all of that installed, I'm going to just check that I have a Hugging Face token set. It's actually set in the environment, so it doesn't request me to put in the token again. That's done via runpod secrets. And I'm going to set some environment variables here for the directory where the model weights should be downloaded. Now, before I go through in detail, let me just give a sketch of what's going to happen. I'm going to train a model. I'm trying to train the model to improve at touch rugby. I've got a data set that has some questions and answers, and I'm going to train the model on that. And then I'm going to test it on an evaluation split. But I want to test it during the training run. Now, the way I'm going to test it is I'm going to grade its answers against the ground truth answers, and I'm going to use a language model to do that. So that's why I'm setting up a judge here. When the judge is set up, then we'll go to fine-tuning. We're going to load a model. Once the model is loaded, we will apply LoRa adapters. We will then load the data sets, and we're going to format the data into the right format for training. I'll talk about that. Then we will look at some of the logic for setting up the trainer. So here we're setting up the training arguments, nothing yet on custom metrics. And then we're going to subclass the trainer to include custom metrics. And we're going to do that by overriding the prediction step. The prediction step is normally where we do the forward passes. And we're going to override that so that it continues to compute the cross-entropy loss, but it will additionally now compute the strings, the output strings, the answers that are coming from the model. And when that's done, we're going to run the training, and we're going to see here our training unfold, and hopefully some of the metrics start to display. So here where the training starts, I think I ran it earlier. We're going to see, we're actually going to test out the metrics first, but we're going to see during the training here as we progress through the steps 3, 6, 9, 12, we're going to see that our accuracy is going up. So here's the accuracy, the judge measured accuracy. We're going from 0.7%, 72%, 86%, and then up as far as 95% correct. So you can see that during the training, our training is having a positive effect because we are getting more of the questions correct. And when that's done, you could then optionally decide to push your model up to hub. So a few things I'll go through in detail. First thing is just the judge setup. I'm not really teaching you much about custom metrics here, so I'll go fairly fast. I'm using the judge to compare the answer, the prediction, and the ground truth answer. So this here is all just setting up taking in the API key, defining the model. We're going to use an OpenAI style endpoint when we call the model, which will be either a Gemini or an OpenAI model. I'm going to use Gemini here. All of this here is just reading in the API key that I need to provide and defining the provider. So I can actually just run that. I'll show you here what it does. Enter your Gemini API key. So let me just pause the video and I'll do that. Okay, so I went over to AI Studio and I got an API key and I put it in. If you ever want to reset the key, you can just put true here. Otherwise, it's going to be stored in a temporary file that's called .provider.env. So anytime you rerun this script, it's not going to ask you for that key again. So we basically just entered the API key. We've said we're using Gemini. We've said we're using Gemini Flash 2.0. You could use a later model 2.5 or maybe 3 if you're watching this video sometime in the future. Now we're going to set up the evaluator. So the evaluator's got a system message saying that it's an expert tasked with determining if an answer satisfies the specified criteria. It will receive a question, the criteria, and the answer. And it needs to give reasoning and then a score of 1 or 0. Then we will pass in the prompt template, which templates the question, the criteria, and the answer. And the model will be asked to respond with reasoning and the score of 1 or 0. So we have then some extraction logic that will pull out that thinking, the reasoning, and the score. And here we have a function that evaluates an answer by taking in question, the criteria, and the ground truth, and the generated answer. And then it's going to template that, pass it in to get chat completion. And then it's going to extract the score and extract the reasoning. So if you want to just quickly test that, there's a test here. What's the capital of France? The answer should be Paris. That's the evaluation criteria. Final answer is the capital of Paris. And if we say here, what's the capital of France? And we say the answer is Lyon, then yeah, the judge fails because the answer says the capital of France is Lyon. And by the way, it's hard coded here to expect that the answer is correct. And that's what's telling us if the judge is working. So we have a judge here and we're going to run this judge in the training loop. So it's going to run during the prediction step of the evaluation. So now I'm going to set up my model. I'm going to set up training. A lot of that will be standard, but what will not be standard is the custom metrics when we start to do that. So this is all pretty usual. We're going to load a Qwen34B model. We are also going to define a dataset to load. I'm using the Trelis Touch Rugby Synth dataset. It's a public dataset you can check out on Hugging Face, and it looks like this. You can see here it's got questions and it's got answers. So actually it doesn't have evaluation criteria. We're just going to use the answer as the evaluation criteria. So it's a little bit of a hack, but we're going to use the answer. So right here, I'm setting the question column. Q column is question, answer column, criteria column is answer. The answer column is also answer. And we are not going to use a different set for evaluation. We're going to split this data set. So I'll run this. I've got some helper functions here that just help me to clear CUDA. It's if you're rerunning cells, you can clear off models that are taking up weights on the GPU. So I clear the model. There's nothing already on the GPU, but I clear it anyway. And then I load up this model. We're going to load it in full precision. Well, 16 bits. You can print out the model to inspect it if you want. And this is a fancy helper function that helps you identify the shape of the layers. This is useful if you want to pick the alpha parameter for LoRa, because technically the alpha parameter should be the square root of the rank of the matrices that you want to fine tune, of the modules you want to fine tune. So technically it allows you to set this LoRa alpha value here. Now the model should just be loading. Okay, it's loaded. Well, it's still loading. The shard should load now. It was downloading. It should print the model. And then we should be able to see the dimensions of that model. And there is Yeah, there is one more thing to say here. There's this extra line that you normally won't see, which is fast inference equals true. And this is what Onslaught does to load the model, but then it connects it wires VLLM up. So VLLM is now using the same weights. And because this is happening, VLLM is going to build CUDA graphs so that it's able to do faster inference. And because of that, it's actually going to take longer to load. So here, even though we've done the standard loading, VLLM is now starting and it's compiling kernels. So we're going to see it continue to compile kernels here. It'll take a minute or two, and then it'll be all loaded up and wired. So when all of that is done, we'll apply some LoRa adapters. We're not training all the weights. We're just training a subset. We're going to train the attention and the MLPs. There's nothing particularly special otherwise than the other videos I make. By the way, if you want to watch a video on synthetic data, you can check that out on the Trelis channel. You'll find it under the fine-tuning playlist. There's an older video explaining how to make synthetic data for training. So the kernel's still compiling there. We'll apply the LoRa adapters. We'll check then how many of the total parameters, now including the adapter parameters, are trainable. Should be a small percentage. And then we'll move to setting up the data set. So here we are setting up the train and the eval data set. We'll then just print out the size of those data sets. And we will check some of the rows. So here is a question, for example, and here's an eval question. Now we're going to format the data. So we have data that's in the format of rows I just showed you here, and we need to get this templated. So we're going to use the tokenizer chat template, and we're going to pass in the user and assistant messages like this. Now notice that I'm not passing a system message, although the tokenizer sometimes adds one. You can see that when we run though and print out a formatted function, there is no system message. So it looks like the tokenizer is not forcing a system message here. And here I have tokenized a full question plus answer, which is why you see here the answer. Now, because we are not using thinking, this is a model, the Quen model, you can use with or without thinking. I have set enable thinking to false, and that's why it has injected these empty think tags here. If you want to use reasoning, you would set that to true. And in that case, it won't inject these tags. But then you would probably need to have some reasoning to inject here. And our data set does not include thinking. So this is not training for a thinking application. Next, there is some setup here. This might look like extra, and it kind of is extra. It's setting up a custom optimizer. And the optimizer schedule here is doing the following. It's warming up. It's then doing constant, and then it's annealing at the very end. So it's kind of ramping, constant, and then annealing. So that's all that this here is doing. It's warming up for the first 1% of steps and starting to anneal at 50% of the steps. Okay, by now we should be loaded. We are loaded. We can see that these are the dimensions here. There is a dimension of 1000. So arguably you should be setting alpha roughly equal to 30 because it's the square root of 1000. And we've loaded the LoRa, print trainable parameters. Not sure why that failed actually. Let's see if maybe I didn't run that cell. So you do need to actually create the parameter efficient fine tuning model. Should just take a second and then print the trainable parameters. I'm glad I went back to run these cells because I missed them. All right, so we have Onslaught additionally doing some patching, and we've got 1.6 parameters of trainable. We'll just print out some of these data rows, which should show the exact same thing I had showing before. We'll test out the formatting. We're running with a virtual batch size of 32, but my batch size is probably smaller. It's probably 4 or 8. Yeah, it's 4. And now we are going to add some common arguments. So things like the training batch size, eval batch size, number of gradient accumulation steps, epochs. We're going to eval every 20% of the steps. We're going to report to TensorBoard. There's nothing here specific to custom metrics. So we'll keep going. And now we're going to fine tune. Now, here's where the tricky part comes in that you need to, oh, it looks like something has stopped working. That's, this always looks concerning, but generally it doesn't cause too much issue. You just need to wait a second and Usually it just kind of goes away. Okay, yeah, I think it's somehow reconnected here. So we just go back in, advanced fine-tuning, fine-tune. That's where we are. Okay, so here we need to change something, because normally when you run a trainer, it's going to run a prediction step. And the prediction step normally is just going to calculate cross-entropy. So it's going to do a calculation like this here, and then it's going to return a loss. But when we have custom metrics, we want to return more information than just the loss. We want to return the token IDs and we want those token IDs to be from autoregressive decoding. So we want to return more than just the loss. And that's why ultimately down here, we want to return what we're predicting. Now, you can also return some labels, which you can think of as ground truth for the autoregressive decoding. There isn't really a ground truth, so labels are kind of meaningless here, but we will return them anyway. Now, the way you decide to subclass something, subclassing means that you take everything that SFT trainer has, which is a ready-made component from the TRL library, and you overwrite some of the things. Namely, what we're overwriting here is the prediction step. If you want to see what SFT trainer normally looks like, you could look at it like this. So you can inspect what prediction step looks like, and you can see here exactly what it does. And yeah, notice that normally prediction step does not have anything autoregressive within it. So the whole point of what we're trying to do is we're trying to write over it with something that includes autoregressive decoding that's going to provide us with strings. Ultimately, it's going to provide us with answers that we can then evaluate. So after we do this somewhat normal returning of cross-entropy loss, we are then going to do autoregressive decoding. And the way we're going to do autoregressive decoding is using this function called generate batches, which is provided by unsloth. And unsloth provides generate batches, and generate batches itself wraps fast inference. And fast inference is a call to VLLM. So yeah, there's a whole hierarchy, but we're going to call generate batches. It's going to call the model via the VLLM engine. It's going to pass in prompts, sampling parameters, and it's going to pass in a LoRa. Now, this is kind of subtle here, but every time we evaluate, we need to evaluate it with VLLM, and VLLM needs to be past the LoRa adapter. And for it to be past the LoRa adapter, we need to actually temporarily save the LoRa adapter and then pass it to VLLM. So that's what's happening here. Every time we validate, we run evaluation, we will save the LoRa adapter that's attached to the model that's being trained, and we'll pass it as a LoRa request to VLLM. If you do not do that, VLLM is just going to run the base model. Don't worry, I spent hours or days running the base model uselessly. So yeah, you need to pass the LoRa adapter. And when you've passed the LoRa adapter, you can then get, basically, you're getting the updated model that you're currently training, which is exactly what you want. So yeah, here we are running VLLM essentially. We're calculating some output tokens, and we are then collecting those tokens. We are padding them, and then we are stacking them up. And these stacked up tokens, sorry, I don't know why it's shutting down on me here. These stacked up tokens are then being returned, and they're going to be returned as part of the prediction batch. Now, you remember earlier I made a comment that we need to pass everything around as tensors, and that's because when we use accelerate, it's used to handling tensors, not strings. So when we run this prediction step, we're going to get a bunch of tokens representing the outputs, and these are what we're going to use in our compute metrics function down here. Well, let me see where my compute metrics function is. I actually am going to have to probably save this and just refresh. Let me just refresh my screen here. And go all the way down, because I want to show you compute metrics. Yeah. So compute metrics is going to take in the predictions, the predicted IDs. We don't actually use the label IDs, but we take in the prediction IDs, and we're going to use them to compare to the ground truths. So we're going to decode them. Here you can see we're decoding them. We're going to decode the ground truths, which are the references here. And then we're going to run an evaluation on those. So you can see here, we're setting up a judge, And we are then going to execute that judge in a thread pool so that we parallelize things, and we're going to evaluate the questions versus the answers. So I know I'm sketching high level, but I'm going to go into a little bit more detail. I just want to sketch the high level of what I'm doing here. So going back up again, when we run the prediction step, we're creating these IDs. Now, there's another subtle point here that I need to mention, which is when we pass the prompts into the LLM, we do not want to pass the prompts including the answer. We only want to include the question portion. And to do that, that's what this logic here is doing. It's filtering out everything that has been labeled with a -100. Now, why does that make sense? To explain why that makes sense, I have to explain something else, which is the following. During fine-tuning, it's common to train only on completions. What that means is if you have a question and an answer, you will roll forward. Actually, it's good if I look here. Let's say that I have a prompt. This is not a good example because it's not a question and answer. But if I take a question here and I say, how are you? And then the answer is, I am fine. When you roll that forward, the model is going to predict the next portion. And here I'm talking about teacher-forced decoding. I'm not talking about auto-regressive decoding yet. But when I roll this forward, I will just have the model predict something. So R, maybe the next thing after you is you, how are you going? Might be the next one there. And then after I, it would be I am fine today. Okay, so these are my teacher-forced predictions. And how cross-entropy works is it compares the ground truth. So I should make this clear here. I should say this is predictions. And then I should say ground truth labels will be just this here, but moved one to the left. Actually, this one here will be moved there. It's easier if I just put it all together. So the ground truth labels are here, the predictions are here, and I'm going to compare pairwise the labels with the predictions. That's what cross-entropy is. And it's going to then sum across each of these comparisons. That's a very high level of what cross-entropy does. Now, it's common, rather than training on cross-entropy on all of these here, it's common to only train on cross-entropy on the outputs. So only make a comparison here on these ones and not care about cross-entropy here. And the reason is because you're not trying to train the model to be good at questions, you're trying it to be good at answering the question. So you really care about accuracy on the answer tokens, not so much on the questions. So if you're doing what's called completions only training, then you're just going to train on these. Now to do that, and I know this is a big digression, to do that, Unsloth have got a helper set up, and we can find that helper by just searching for completions, I think. Only. I'm looking for keywords and I'm not finding them, but I know where the script is because it's down just always towards the trainer. So basically the way that Unsloth knows to train only on completions is it will template the whole thing. So here you have the user prompt, what organization led the review of domestic playing rules for touch football? And then you've got the assistant here, and this is all the assistant response. And the way that you train only on completions is what you do is you detect everything up to and including the assistant portion of the response, which is demarcated by this I am start assistant think. And everything here you just assign a -100, and -100 means it's ignored in the cross-entropy loss. So this is how you apply the mask. And actually, if you apply the mask based on that, you'll see here if we're using the Quen model, it's going to use this here to detect the end of the user's response. So it's using this then to basically hide out all of the question. And you can see exactly here, I've printed things out. This is based on script by Unsloth, this part. All of the user part, including up to the end of think is hidden out, and it just starts here. So we use the -100 tokens to indicate that the cross-entropy loss should be ignored there. But because the -100 helps you here for this portion, we can use that to identify the question portion of this data. And the question portion is what we need to roll forward on compute metrics. So that's why when you go all the way back here to the custom predict, and sorry, the custom prediction is, let's see where it is, it's here. You'll see that when we assemble the prompt, we are using the -100 to pull out the prompt that we want. And that prompt then is being passed in ultimately here to generate the batches. Okay, so we are detecting the prompt portion. We're sending it into generate batches. Generate batches calls fast inference, which calls VLLM. If you want to look at generate batches, by the way, you can do that by uncommenting here. So here is generate batches, and it's an unslot function. And yeah, it basically allows you to create some batches and run LLM generate. And LLM generate is a VLLM function. And it does this thing here, which is basically resizing the batch size. So VLLM does automatic batching. If you send in a batch of 1 million requests to VLLM, it will actually not process them all. It will process them in batches. And it will determine the batch size based on the memory available when it initially loads, which will only consider the initial sequence length. It will not fully consider the added length, I believe, for decoding. And this can lead to out-of-memory errors. So Unslot takes an even more conservative approach and kind of does batching on top of the batching. So it will make its own batches first, send them to VLLM, and allow VLLM to batch from there. And this is very rough. These are very rough heuristics here based on the total memory available. It's calculating how to scale the number of batches. So yeah, that's how you can inspect there. And that kind of wraps up the really high level description of subclassing SFT trainer. So we have a custom prediction step. The custom prediction step will do cross-entropy, but it will also do these forward rolls, these rolls forward using the VLLM engine. And then we will be able to compute custom metrics, which we will have calculated down here. And these custom metrics are essentially taking in the tokens, decoding them, and then taking the decoded tokens and using those to draw comparisons via Gemini, who is our judge. Okay, so with all of that, we can go to training, but something that's really useful is before going training, you want to check your metrics are working. And to do that, you can just run trainer.evaluate. And it's going to create a data set. You can put in a random prefix here. You could even call it just, pre-training test. It's going to append that before the training, before the name of the results. And if you run this, it will just run one evaluation. And this is a really good idea because it gives you baseline performance. And you can see here, it's maybe not very neatly formatted, but before any training at all, we can see what percentage of the questions it's getting right. You can see here the dev judge scores are true, true, false, false, true, 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 false, 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 true, true, false. Okay, there's a lot. And when it puts all that together, it's getting 68%. So the baseline score before training is 68%. And the whole idea then is once we start training, that will hopefully go up. You can see I've printed out debug here. So I'm printing out some of the answers. So you could manually inspect if you want. So then, as Unslot typically does, we can print some stats about the GPU, and we can print some stats on the eval dataset. There are 22 rows here, and then we can train. And when we train, because of how I've set up compute metrics, and by the way, I should have maybe shown that in the compute metrics function, we're returning a few things. We're returning the judge accuracy, which is the average across all the tasks. We're returning an array of the scores, or maybe it's a list. We're returning the 0th prediction just so we can read it, the 0th prediction reason, and then we're returning the first 50 characters of the 0th prediction and the last 50 characters. Now, maybe that's not needed because we're already returning the full prediction to read, but before I was including the full thing, I was just looking at the first and last characters. So when you do run the training, you should see training loss should be falling, which it is here. 114, 0.83, 0.64, 0.61. The validation loss is also falling, 0.98, 0.82, 0.72. And the score is going up, which I already showed you, but it was 68 before training, now it's 72. There's probably some noise in there, but still 86, 95. So you can see things are improving. You can see more of these are true, which makes sense because that's where the accuracy comes from. And you can also see the answers. So, the initial prediction is like this. This is the reason. Sorry, the reason, by the way, is not the reasoning from the model. It's the reason provided by the judge as to why the answer is correct. And yeah, you can see as we go on here, we're just getting answers back and the model is improving in performance. So once that's done, you can print out and see your GPU usage, and then you can decide to potentially save the model in merged format, or you can potentially merge it. If you want to do push to hub merged, you can use this unslot function here. And that pretty much wraps up how to do custom metrics. It is somewhat complex, but it also is fruitful because you actually know where performance is. Validation loss is good to know about because it should be going down. If it starts to go up, you're overfitting. But sometimes it's hard to think about what a meaningful data set is for considering validation loss, and you care more about correctness. And that's really where running something like this, where you have an update on the percentage correct, ends up being quite useful. Now, I'll just say one more thing, which is around memory management. It will take more memory because you're using up KV cache for VLLM. So when you're trying to run a script like this, you want to be careful to set a batch size that's going to be sufficiently small. I think I set the batch size. It's probably starting down here in the fine-tuning section. Let me see if I can find it. Batch size. So yeah, here we have batch size is 4, so fairly small. Reduce it if you're out of VRAM. And what can be nice to do is just also make sure that, the problem actually with VLLM is that when you load the model initially with unslot, it will take up the GPU memory, and then VLLM will kind of use the rest of what's available. And that can be a problem because you end up needing even more memory when training starts, and that can cause you to go out of VRAM. So the workaround for that is when VLLM is started, you can specify a maximum GPU utilization. So I want to see if I've actually specified that here. Max GPU. Let's see if there's a max utilization. And I actually don't have it, so max GPU utilization. So if you go to VLLM, yeah, GPU memory utilization is this one here. So what you can do is, I guess I just was running a small model, so I didn't hit this problem. But what you can do is go back up to where the model is and where I'm loading it here. Let's see. Sorry, I've got so much scripting here for the judge, but I just want to load the model. Yeah. So when I load here, you can load with GPU utilization and set it something like 0.3. And when it loads, this is going to reduce the max number of sequences. So you can see here, it's allowing for 256 sequences. But if you reduce the max GPU utilization, it's going to leave more of the GPU empty, which is good because you won't overflow during training. And it will reduce the max sequences. But 256 is already loads, because if you're running a validation set of 32, then you're never going to need to run more than that anyway. So yeah, you can just add in this parameter here. There is also the ability to put in max num sequences. I can't remember if it's max. It might be num max sequences or max num seq. But if you put that in, I believe there might be a bug in Unslot currently whereby it doesn't end up passing that information. There's some weird combinations of the max num sequences and GPU memory utilization that end up clashing, and doesn't actually get transmitted into VLLM. So just be careful with that. I would recommend just setting GPU memory utilization. I've tested this one. This is the one I use in other scripts when I was trying to do the custom metrics. So that is it for custom metrics. You can find these scripts. It is a pretty advanced kind of thing. I wouldn't recommend doing it if you're getting started with fine tuning. Just do standard cross entropy loss. You can find these scripts in Trelis.com. Just go to Trelis.com and find advanced fine tuning, or go to Trelis.com/advanced-fine-tuning. As usual, let me know if you have any questions below in the comments, folks. Cheers.